Okay, section 2.2, and here we want to look at rotation matrices in R2. So this is the first example of a linear transformation they give. And the idea is simply that if I think of a point out here as a vector, so I go from the origin out to that point, then it could be that what I would like to do is just say rotate that point up here, thinking of it as that, and get a new point, right? And so, you know, why would I ever want to do that? Well, actually, all sorts of reasons. You know, the funner ones, of course, are things like animation of images. But other reasons are just to switch coordinate systems relative to where you are. Okay, so switch coordinates. And so, for instance, I may want to get the area of an ellipse. That's actually something I'm very interested in right now. And actually, if the ellipse is oriented like this, I can get the area of that ellipse pretty easily. But, you know, if that ellipse is like this, you know, it might be a little harder. Well, so what you can do, though, is you can take these points and think of all these points and do a rotation and rotate down clockwise, you know, this angle, and then all of a sudden I'm back to this picture, and oh, then I know how to find the area of an ellipse. And so, you know, in essence, that's kind of what we do when we work with a lot of geometric figures. So what is a rotation matrix? Rotate by theta counterclockwise. Okay, so if that's what I want to do, my matrix is cosine theta minus sine theta, sine theta, and cosine theta. And so, you know, let's kind of check that. Is let's say you know, I've got the situation. Let's just look at a point like a nice simple one, like 1, 0. And if I wanted to rotate that by 45 degrees up to here, you know, so there's pi over 4, you know, then, well, I know that that point ought to be then the square root of 2 over 2, the square root of 2 over 2. Okay, and let's check out this matrix to see what happens. Well, okay, so theta equals pi over 4. Then cosine theta, cosine of pi over 4 is the square root of 2 over 2. Sine theta is also the square root of 2 over 2. And so our matrix A is the matrix square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, and square root of 2 over 2. I guess I didn't really need those commas in there. So there's my matrix A, because I have cosine minus sine, sine and cosine. And so then if I take A times the vector 1, 0. Okay, so that's my square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, and square root of 2 over 2, all times 1, 0. Well, actually, from what we just did with that previous remark, I know I just get the first column as my vector, right? Because I'll take the first row here times 1, 0, or dotted with 1, 0, and I'll get square root of 2 over 2, and then the second row dotted with 1, 0, and I get the square root of 2 over 2. And so, yep, there's my xy point, square root of 2 over 2, square root of 2 over 2. Now, what happens, though, if we rotate it by another 45 degrees? And so let's take, whoops, I'm not sure what I just did. There's a little thing there that, oh, it's trying to, select all text. Copy. Okay. Did it get rid of it? I don't know. No, it's still there. So I need to somehow, I don't know if I can get rid of this or not. I may have to stop this video and start it again. Add favors break. I don't know. Let's see. I'm going to try this. I'm going to try saving the file. Samsung Notes file. Okay. And save. Did that get me out of everything? Yes, it did. Great. Okay. So, sorry about that. Not sure what I hit, but it was, oh, I see. I've got this thing up here. Maybe I was just in a bit wrong mode up in the top up there. At any rate, okay, so let's do that again. Let's take A times the square root of 2 over 2 and the square root of 2 over 2. So we've got square root of 2, a lot of square root of 2, square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, and square root of 2 over 2. So there's the matrix A times my vector, square root of 2 over 2, and square root of 2 over 2. So the first row dotted with that column, I bet I can fit it there. So that first row in that column, I have square root of 2 over 2 times square root of 2 over 2, and then minus square root of 2 over 2 times square root of 2 over 2. So I just get 0. And then for the second row times that column, I'll get square root of 2 over 2 squared plus the square root of 2 over 2 squared. But that then is just, I get 2 over 4 plus 2 over 4, I get 1. And so that's the 0.01, but that's correct, right? Because what we did, we started here at 1, 0. We rotated by 45 degrees, or pi over 4, and we got here to square root of 2 over 2, and square root of 2 over 2. And then we did it again. We rotated by pi over 4, but that would put me up here. I rotated a total of 90, and that is the 0.01. And that is indeed where we got to. Alrighty, so that is the idea of a rotation. And since it's just a matrix multiplication, I know that it's a linear transformation. Now, we can do other things. So, for instance, with the rotation, if I rotate an object, right? So if all points, so if I got an object out here and I want to rotate it down to here, you see, well, I'll get something similar, I guess. I'll bring that down that far, whatever this angle is that I'm rotating this through. So I can rotate a whole figure. But then you can also do other things besides just the rotation. You could scale something as well, and so there's I could scale, and I could scale in different directions and so forth. So if I just use the cosine and sines, it's what we would call a rigid rotation. But notice that I can scale along various directions, and so suppose I let a equal 2, 0, 0, 1/2. What happens to say a square, and if I do something like that? Okay, so let's just take this square. There's 1, there's 1, so this is the point 1, 1 up here. We can look at the corners. So if I have the corners, I have 0, 0, I have 1, 0 here, and 0, 1 there. And so I could look at what A does to each of those corners. So A times 0, 0, well, anything times the 0 vector gives me 0, 0, so that didn't do anything. A times 1, 0, well, that I know gives me the first column of A, so that gives me 2, 0. Then A times 1, 1, well, that I actually need to probably write this out here. Times 1, 1. Oh, but, right, that just gives me 2 for the first component, and then 1/2 for the second component. And then A times 0, 1. That gives me the second column of A, so that's 0, 1/2. And so now there I can look at those vectors as my 4 corner points. And if I do that, what has this scaling transformation done? Well, I still have something at 0, 0. Then the 1, 0 became 2, 0. So maybe I'm out here at 2, 0. And then I was at 2, 1/2. So 2 and just here 1/2. So 2 and 1/2. And then I was finally at 0 and 1/2. And so you see what happened was I took the square and I made it half the, here's the original square, and I made it half the height and twice the width. Okay, so we can do things with scaling. If you toss in non-zero things here on the off diagonals, we can get things like parallelograms and that sort of thing. But I think that's enough with the rotation and scaling, so we'll call that video done.